Hi everybody, welcome to the lecture in downstream processing in biotechnology. This lecture is the last section of the crystallization. Last lecture we talked about the continuous art crystallizer, but now we will focus on the batch crystallizer. The batch crystallizer, if we talk about the population balance, the batch crystallizer, and also the growth rate is independent of the size. That means the population balance is similar to the continuous architecture, but except n is a function of L, function of time, right? If we talk about this is the population balance for continuous architecture, dn by dl plus f over vg multiply n. But for this case, n is a function of L and t also for the batch, and there is no flow rate because the batch architecture is no flow in, flow out. It only initially solution, and then we get the crystal in the solution. There is no flow out, no feed for the batch crystallizer. Okay, we cancel this term, and also dn by dl, and another term is dn by dt for batch crystallizer. Like shown in this slide, this is the batch crystallizer is a function of time. Population density function of time, and population density is a function of length. And G for this case, we assume it independent of the size. For this case, the better technique we call it is the partial differential equation with respect to time and length. It's difficult to determine. The easy way we can reduce from the partial differential equation to be the ordinary differential equation. We can apply the moment method that we define the k moment mu k is defined as integrate 0 to infinity nl l power k dl. And the birth rate, the average birth rate is calculated is equal to delta mu 0 divided by delta t. And also growth rate is calculated with the delta mu 1 divided by mu 0 delta t. What the mu 0 and mu 1? Mu 0 and mu 1. Mu 0 means mu k. K is 0 for this case. Mu 0 equal to integrate 0 to infinity nl l power 0. That means mu 0 equal to integrate nl dl. For mu1 mean mu k integrate equal to integrate 0 to infinity nl l power 1 dl. This is mu1. And also we can calculate average. This is the birth rate, this is the growth rate. We can calculate based on moments. This is a moment about the origin. That's a moment about the origin. This is delta mu 0, delta mu 1. And for average, equal to mu 1 divided by mu 2. For this case, we can conclude that mu 0 is mean the total length. It means the total length. Mu 1 is the mu 0 is the total number. Mu 1 is the total length. Total length divided by total number we equal to average length, average size. Is the mu1 is total number equal to indicate NL, L, DL. Total number indicate NL, DL for this case. And the fraction of total number of the crystal between size 0 and size L. For size 0, we indicate 0 to infinity. For this case, is 0 to L. This is the fraction from 0 to L divided by the total. This is the total. Is the fraction of total number of the crystal between 0 size to size L. And we can conclude in the table. We can conclude in the table for mu 0. Mu 0 equal to integrate n0, nl dl. For mu 1, for this is the mu 0 is the total number of crystal. Integrate 0 to infinity. This indicate at L equal to 0 or L equal to infinity. Sometimes for the crystallizer, maybe it's not initial, it's not start from 0, right? And the final is not infinity. For example, If we plot L and fraction, right? Sometimes length is not start from 0. We can indicate from this to this as I not 0. It may be from 10 to 100, for example. It may be like this. But in the length, it should be 0 to infinity. It's a general rank from 0 to infinity, but depend on our system. If our system from this L1 to L2, it may indicate from L1 to L2. This is the definition. Whereas mu0 is the total length, total number of the crystal integrate in LDL. And mu1 is the total size or total length of the crystal indicate NLLDL. For this case, as the average value for the spherical crystal mu1 divided by mu L. Okay, mu2 indicate NLL squared DL. Mu3 indicate NLL cubic DL. For this case, represent the mass of crystal. It represent area of crystal. If you multiply mu2 with shape factor, that's like Ka shape factor and mu 2L square. This is area of crystal. Right. And also for this, if you multiply low KVL over 3, this is mass of crystal. Low KVL over 3. This is the low density or mass of crystal for that case. If you know like the size distribution, like previously, you know like n is a function of L, like P the continuous was it? You know the n is a function of L, and then you can integrate NLDL. And also you know L is a function of L. You can integrate this by numerical or by analytical technique. And then you can calculate mu1, mu0. Mu0 is the total number. Mu1 is total length or total size. Mu2 is the area, which is equal to K A mu2 L square equal to total area. And our mu3 multiply low this mu3 also. Multiply mu3. That's right. Low KVL power 3 multiply mu3. This is the mass of crystal. For the case, you can obtain this from the back crystallizer. And the last topic for this, the scale up of the crystallizer. Scale up the crystallizer, mostly we will scale up from the laboratory scale of for the small scale. We would like to generate the same condition. Batch scale, small scale, large scale, or laboratory scale to the industrial scale. The condition should be the same, and the geometry also should be the same. We call it the geometry similarity. That's right. Mostly in the scale up, the crystallizer scale up is about 50 to 500 fraction from the labs to the pilot scale or industrial scale. For this case, mostly we apply the geometry similarity and constant power per volume. What does it mean? For the lab scale, the geometry of crystallizer should be the same large scale, and the power per volume used in lab scale also is the same in the large scale. For this case, we can apply the formula like for the turbulent flow that's Reynolds number greater than 10,000. The power per volume mean that P over V proportional to the N power 3D power 2 N is the impeller speed. That's like impeller rotation rate or impeller speed. Di mean the impeller diameter. We can use this as the formula to scale up. P over V proportional to the Ni power 3 Di power 2. And also this depend on the turbulent flow. You have to check this turbulent or not. You can calculate the Reynolds number. This Reynolds number not the same as the Reynolds number in the flow in the tube or the pipe. This Reynolds based on the impeller by the mixing oxidation. That means impeller For that case, Lenovo equal to di square ni low divided by mu. Di mean impeller diameter, ni is the impeller speed. Low is the density of fluid, mu is density of fluid. You have to check this greater than 10,000 or not. If it's greater than 10,000, you can use this formula to scale up. And another technique for the scale up, you can use the constant imperative speed like NITI is constant. This means NITI from the large scale or small scale should be equal large scale or inductive scale. And also you can use the minimum speed required for particle suspension by this relation. For this, if you use this relationship, NITI power 0.85 is constant, that means it equal large scale and power scale. These two criterion that I should keep both secondary nucleation, crystal growth rate are more or less independent of the scale operation. That's it, the secondary and growth is less independent. It maybe depend on the crystallizer. Okay, form analysis of the data of the crystallization at laboratory scale or pilot scale. The scale up equation that's proved to be more accurate in describing laboratory. That means the equation should prove accurately from laboratory scale to the scale up or to larger scale. However, the flexibility should be designed into the plant unit. So aggregation layers, flow layers, it may be vary for that case. In the small scale and large scale, sometimes the flexibility should be considered for the aggregation layer and flow layer. It's not necessarily exactly the same. Exactly the same for lab scale, small scale, and the large scale or industrial scale. This is maybe the error in the scale up to larger scale because of the effect of change in concentration or impurity in the starting solution maybe help on the operation because the lab scale and large scale. The large scale mostly we use the industrial scale. Sometimes the impurity is higher than the lab scale because the lab scale will be easy to manage the feed, manage the initial concentration of impurity. That means there are sometimes different in flow rate or aggregation rate for the lab scale and large scale. Okay, for the last example, that I need to determine the scale up of crystallization based on constant power per volume. For this case, we would like to scale up a batch crystallization of antibiotic based on experiment in 1 liter crystallizer. For this case, the use of 3 cm in diameter of impeller at speed of 800 rounds per minute led to good crystallization result. Okay, for scale up, you maintain the power per volume constant to scale up from 1 liter to 300 liters. What should be the diameter and speed of large scale? Okay. In this case, the solvent has the same density and viscosity of water. We assume the density of solvent is the same as water. Okay, for the scale up, we assume geometric similarity is the same geometry of the crystallizer. The volume scale and impeller diameter should be proportional, right? We should be proportional to the diameter of the impeller. For that case, we can approximate V equal to diameter power 3. That means if we denote 1 is the large scale or small scale, 2 is the large scale. The ratio of V large scale to small scale equal to the ratio of impeller diameter of large scale and small scale. All of this is power 3. That means for this case, you can determine the diameter of large scale from this relation. The diameter of the small scale is 3 centimeter and volume of large scale is 300 liters. Small scale is 100 liters. You get 20.1 centimeter. This is the diameter of impeller. Okay, you know the diameter of impeller. You can use the power per volume to be constant. For the power per volume to be constant, that means Ni power t di power t of lab scale or small scale equal to ni power t of di power 2 of the large scale But we will use this relation. You have to check the Reynolds number is greater than 10,000 or not. If you use this equation, okay, you have to check the Reynolds number. Reynolds number di for the small scale is 3 centimeter square. Ni is 800 revolution per minute, and multiply density. Density is absolute is water 1 gram per cubic centimeter, and convert from minute to second. That's it. Divided by mu. Because the water is 0.01 gram per centimeter second, you get 12,000. This is greater than 10,000. You can use this relation. You can use this relation to calculate impulse speed of the large scale. You know the diameter of large scale, diameter of small scale, and impulse speed of the small scale. And then you can solve for impulse speed of the large scale. That means 225 per revolution per minute. You can see that if we increase the size of cursor is larger, the impulse speed will drop or will decrease. This is the common sense. At larger size, the speed should be lower. If we use everything the same, the speed should be lower for that case. So thank you for your attention. For this case, it's the last slide and it's the last section for the crystallization. Okay, thank you for your attention. See you for the next lecture on the chromatography.